research roundup. And so each person is going to go for 1 minute, and we need to stick to this timeline if we want to have time to discuss the state of the art afterwards. And we'll tell you when you have 10 seconds left by saying 10, and then you should try to wrap up. We've given you all little sheets of papers with a name. So since you can, there should be one per row. And if you can find your name, you can come on this side, for example, right before it's your turn, so we can have a smooth transition from person to person. And we'll have a break at 10:20. So we'll go for 15 minutes now, approximately. And the first person to speak is Megan Leclerc.
Okay, thank you. Hi. So I look at climate change in Africa, looking at precipitation and aridity in global climate models. I'm going to start by talking about these illustrations. These are from a Congolese artist. I asked him to draw some pictures of climate impacts on different sectors in African economy, and this is his agricultural drawing. So there's a few different themes here of climate impacts on the agriculture system, and this is what I try to keep in mind when I think about my research on a day-to-day basis. I look at large ensembles of GCMs. There are changes in climate across these GCMs, in precipitation and aridity specifically, and right now I'm trying to understand why there's differences across these models. So is it structural changes within the model, or structural changes across models, or variability that can be captured by multiple runs in the same model? And I think that's 1 minute.
Okay, I'm Ludwig Hillary, and I teach meteorology, but I like to teach with the observation. So I'm interested in the large-scale dynamics, particularly interested in extreme weather events. I put up there some typhoon and blizzard. I actually leave the hurricane to Kerry. I'm more interested in the middle latitude system and the role of the middle latitude in the large-scale anomalies. Like, for example, the winter of 2015, we all enjoyed the snowfall, and I particularly enjoyed it because it was a very unusual winter, and you try to understand why. And the reason is behind the kind of pattern, a stationary pattern called blocking. If you remember, it was extremely warm over, already? Okay, so to let you know there are other outreach activities that I do, and introduction to weather forecasting in IFE, open to everyone. And that's
John Marshall. When I get excited about something, I always start drawing on my blackboard, and I was trying to prepare my overhead, and I thought, bugger it, I'll just take a photograph of it. and so I'm in the last 10 years or so, I've been thinking about coupled climate dynamics. So I'm thinking, I try to artfully simplify things. So I look at the atmosphere and its coupling to the ocean. I'm interested in ACC, Intertropical Convergence Zone, the two poles, and particularly the response of this system to impulsive changes in greenhouse gases, ozone, volcanoes, hemispheric asymmetries in climate. Why is it warmer in one hemisphere than the other, and how does that affect the ITCZ? And also the possibility of multiple equilibria in climate. I can't do anything on my own, and I collaborate with many people. And here's a list of my collaborators on this project. Thank you.
Hi everyone, I'm Tristan. I'm a first-year graduate student. I got my bachelor's degree in computer science last year from the University of Wisconsin-Madison and spent some time there trying to understand autocorrelations in a very simple model for tropical precipitation. Here I'm working with Tim Cronin. My table mates this morning were encouraging me to announce that I was going to solve convection while I was here, but that seems like far too large a snake to defeat in the next 5 years. So I'll just say that I'm trying to understand aspects of convection and how they couple with larger scale circulation patterns.
I'm Vince Sagard. I'm a PhD student in Carrie's group. Can you play the video? Hopefully.
What's your video?
Yeah. There we go. Cool. So I'm studying also convection, severe convection in continental mid-latitudes in the context of climate. And the way we're doing that is by looking at convective available potential energy, or CAPE. This is a movie of CAPE from a reanalysis data set over a time lapse over the whole year. And what you'll notice is that we have these extreme peak values of CAPE that come in mid-latitudes, like here in North America. You can see it's happening. We get these extreme peak values that can get really severe storms. And we want to know, why is it there? Why is it that magnitude? So that's what I'm looking at.
Hi, I'm Oliver Andrews from UEA. I'm visiting MIT for 3 months. I think my slide might be a bit complicated to tackle in 1 minute, so I'll just say that I'm here and I'm interested in detecting climate influences. So the upper plot summarizes a method that I use, which is called detection attribution, and I'm interested in how historical changes in greenhouse gas forcing can drive changes in ventilation. And the lower plots show changes on the left in oxygen, so ocean deoxygenation over the historical period. And I'm interested in how that relates to changes in greenhouse gas forcing. And so if you would like to collaborate during the next 3 months on oxygen and carbon in the ocean, changes in ventilation, or indeed the fluxes that I'm showing on the right of marine nitrous oxide, so nitrous oxide production in response to changes in oxygen. Thanks. Then let me know. I'm here until Christmas. Thanks.
Okay, so Mohammed, my name. Working on new method based on machine learning algorithm to detect, track, and characterize eddies. It's fairly simple. It basically gets a flow field, dystrophic flow field, and you calculate that phi thing, which is basically direction of the velocity field. And then eddies turn out to be, in phase space, they turn out to be this sort of distinct rainbow structure. So you train models to detect those. And then the advantage of this method compared to the conventional method is that basically it eliminates totally the misclassification problem, if you know what it is. And then also it's parameter free, so it certainly doesn't need tuning as you go to different directions. 10 seconds, okay. And then finally, we built a front-end program for that, so basically it's an atlas of eddies. And it's co-localized with other data sets like temperature, cold field, and things like that, so we can get those.
So I decided I should just make a simplified version of the marine nitrogen cycle and put that up. So each of these different compounds, nitrogen-containing compounds, exist in the ocean. Each arrow is a different microbe that converts one form to another. And I study how all of this works. Some of these forms are available to life, some of them are inert, some of them destroy ozone, some of them are greenhouse gases. And really I study how this whole system manifests and the controls of the different microbes that do this. And how it feeds back on climate, which is why I'm in PAOC.
I'm Lydia. I'm a first-year research to talk about, but I graduated from the University of Georgia this past May, and I got my bachelor's and my master's through this combined degree program. So for my undergraduate senior thesis, I worked on marine photochemistry and the photochemical production of hydrogen peroxide and carbon monoxide. And then my master's thesis was in marine organic geochemistry. So I looked at the BP oil spill and petrogenic compounds in the sediments there. And also I looked at coral reefs in the Florida Keys and how they were responding to thermal stress.
Hey, I'm Santiago Benavides. I'm a first year in atmospheric science working with Glenn. Since I don't have exactly like a research topic right now, I'll talk about what I did before and what I'm currently interested in. So I just did a year master's in Paris working with Alexandros Alexakis, where we studied thin layer turbulence and we looked at when the inverse cascade begins and how this transition occurs. And I'm currently interested in looking at turbulence on giant planets with Glenn, dealing with zonal jets, polar vortices, or in general how the different forcings look and what they might tell us about the underlying structure.
Hi, I'm Tom Buchler. I'm a third-year PhD student working with Kerry Emanuel and Timothy Cronin. And for my thesis, I'm looking at the interaction between the radiation, so the sun, the water vapor, which I've represented falsely with a droplet here, a cloud, and the surface and atmospheric convection in general. And hopefully the goal is to see how that participates in the physics of how water vapor aggregates isotropic at scales of 100 kilometers roughly. And so right now I'm studying the left question mark, the red one, and hopefully by the end of this year or in a year or two, I'll be studying the black question mark. So thank you very much, and anyone who wants to collaborate, I'm on the 16th floor.
Hi, I'm Jörn Kallis, and I study right now the dynamics of the deep ocean circulation, in particular the circulation below 2,000 meters, where small-scale mixing helps drive the large-scale overflow of the ocean. And in particular, we're starting to appreciate that waters are not uniformly upwelling throughout the ocean, but that boundary layers on slopes, as I sketched on the right here, play an important role in this circulation. So I tried to put that into a dynamical framework. As you see on the bottom, I tried to study oceans that look more like bathtubs instead of shoeboxes, and I try to understand the fundamental physics of how the circulation works.
Good morning, everybody. I'm Jean-Michel Champagne. I'm working on MIT GCM. So there is a nice introduction of the different things that you can do with MIT GCM on the website, where Ellen has been putting updates every month of nice story. And I'm interested in different aspects of it, numerics, so it's illustrated here a little bit with this schematic view of the time stepping. I'm doing many test cases and validate and to see how the scheme performs. And from time to time, I'm doing also some idealized simulation where you can see analyze the different diagnostics of fluid and how the moment performs. So I invite you to look at the website and to have an idea of how the different applications work. Thank you.
The video went on autoplay. Anyway, my name is Christine, and I'm a graduate student working with Professor David McGee. And as a paleoclimatologist, I'm interested in the history of Earth's rainfall patterns. And for my current project, I'm reconstructing past changes in the South American summer monsoon by studying high-altitude ancient lakes in the central Andes. Today this region is super dry, but from satellite imagery, we can tell that that wasn't always the case. Here you can see a bunch of these well-preserved paleocean lands that look like amazingly preserved bathtub-like rings. And these lines were formed by enormous lakes that no longer exist today. But what's special about these basins is that since they're landlocked, that you can think of them as Earth's natural rain gauges. Their lake levels are going to be directly related to changes in precipitation and evaporation. So if we know when they existed and how big they were, then we can reconstruct what rainfall was like in the past. So, thank you very much.
Hi, I'm Susie Clark. I am a physical oceanography student in the joint program with Woods Hole. My advisor is Steve Elbar in ocean engineering. My research question revolves around how do sea level, tides, waves, and storm surge affect the flux of groundwater to the ocean. And we're attempting to answer this question with a series of 32 groundwater wells on a barrier island in the Outer Banks of North Carolina. And that's the top image, and then the bottom image is a cross-section of the groundwater wells. I'm looking at groundwater head dynamics, and I'm measuring submarine groundwater discharge, which is the flux of the groundwater below the ocean surface to the ocean, by using radon and radium isotope tracers and applying that to a chemistry model. So it's a mix of the hydrology, the physics, and the chemistry. Thank you.
I'm Tim Cronin. I'm an assistant professor of atmospheric science. I started. I was here as a student a number of years ago, and it's great to be back. I like to think about problems of the role of the atmosphere in the climate system and land-atmosphere interaction, especially idealized problems of weather and climate, both in the tropics and at high latitudes. So I'm sketching out a problem here of how very cold air forms. So you start with air over an ocean surface and it moves over land during a polar night, and there's no sun to illuminate it. How does it cool in time? Really simple problem. Not many people have looked at how this changes with climate. So what I'm showing in the schematic here is that how a temperature profile evolves with time, and then in orange colors that surface cooling is weaker in a warmer world, and that may be an important factor of climate change. So I like to think about problems like this if you're interested. Talk to me. Thanks.
Good morning, I'm Dan Sitso, and our group is organized around two different things predominantly. First off, we build and deploy instruments to the atmosphere to understand the particulate matter that's in the atmosphere and the clouds that they spawn. And this is work that you'll hear a little bit more from Michael and Maria about. We make those measurements and then we bring that information back to the laboratory because it's critical to understand what particles actually exist in the atmosphere before you do experiments on it. Otherwise, you can fool yourself into using the wrong materials. And so Sarvesh, who just graduated, and Martin, who's taking over from him, deploy a set of cloud chambers to understanding activation conditions of those particles. And then this is the feedstock that we put into models. This is something that we can't do in our group, but we're very lucky to have a visiting scientist, Muge, who you're going to hear from later, and also collaborate with Chen's group and Daniel Rothenberg on this type of thing to understand the climate implications of these particles. And I'm in 50 seconds, so thank you.
My name is Amy Dale. I'm a new postdoc in Susan Solomon's group, also collaborating with Ken Strausbach in the Joint Program on the Science and Policy of Global Change. My research focuses on integrated environmental models to better understand the impact of climate change on agricultural production and water for agriculture in sub-Saharan Africa. So I work with crop models. I'm building crop models and hydrologic and water resource models to interface with general circulation models and global soil data. I'm particularly interested in the effect of uncertainty and how we can capture model uncertainty in these models. And a long-term goal is to explore the benefits and limitations of irrigation as an adaptation strategy in different regions. So, thank you.
Hi. My name is Gino. I joined EAPS 5 years ago now, more than that, thanks to Sarah. I'm an engineer, and then I drift towards studying other planets of the world. So, two things. I developed a technique to study them. I'm going to talk about two of them. that we developed and then applied. On the right side, yeah, everything is showed at the same time. Okay, good. On the right side, we have the first cloud map of an exoplanet, which we use to get the very first insight into what's going on over there. So think about this planet steadily, like totally the same phase show to its star, and you have this particle of air that is really hot, goes to the night side where it condenses, and then goes back to the day side following the water, and it just allows it to sustain this constant cloud coverage on one side, which you saw up here, top left for you. Then at the bottom you have the very first map of Earth-sized, super-Earth exoplanet, which appears to be a lava world, so you do have a massive amount of lava on one side of it. Then on the other end, we do have transmission spectroscopy, which we use to gain insight into Earth, into these planets, looking at how the light changes when it goes through the. Yep, done. Okay.
Hi, I'm Andre Drake. I'm a first-year grad student in the joint program in physical oceanography. So my previous work, so actually first, I'm interested in the meridional or returning circulation in the ocean. And so I'm mostly interested in the upwelling limb of that. And so there's two parts. There's the diabatic upwelling and the adiabatic upwelling. So I've previously done work on the adiabatic upwelling. So this is a movie of Lagrangian particle trajectories from a high-resolution ocean model showing the adiabatic upwelling in the Southern Ocean, driven by the winds and the sloping ice signals. And then on the right is work that I'm starting now in Raphael Ferrari's group, looking at the same process that Jörn Callies talked about earlier. So mixing driven upwelling along boundaries in the ocean, and I'm hoping to connect that to observed tracer distributions. Yeah, so thanks.
I'm Margaret Duffy. I'm a second year in PAC, and I'm working on two different projects. So I did two different Lubavitch churches to prepare for this. So my primary project is studying tropical precipitation and how it changes with climate change using really simple models. And my second project is modeling the distribution of copper in the ocean. This is not what copper in the ocean looks like. It's a trace metal in the ocean. But we're hoping to ultimately have that model built into the MIT GCM. So if you're interested in either of these topics and want to come talk to me, please say hi. My office is on the 15th floor.
I'm Stephanie Dukevich. I'm a principal research scientist. My research interests are on the marine ecosystem, and one of the main tools I use is an ecosystem model. The movie I'm showing is showing diversity in this particular numerical model, which is shown there as the number of coexisting species. And you can see how dynamic it is, so how important this three-dimensional ocean transform mixing is. But it also, that diversity is really set by various different things that are different about phytoplankton. In fact, the difference in size, different in function, different amount of pigments. And so trying to understand, a lot of what I do is trying to understand how different controls from physics, from nutrients, from grazes, will set these patterns.
Hello, I'm John Dwyer. I'm a postdoc here working with Paulo Gorman. And one of the problems we're working on is to use machine learning to model convection. So the idea is that one of the most uncertain parts of large-scale global climate models is the convection scheme. So the idea is to apply a neural network where other machine learning techniques where you learn on a finer scale model that can explicitly resolve convection. And then you take your learned network and put that back into the larger global climate model, so that might be better at doing convection. So the first step that I'm working on is just taking, just training, instead of on the finer resolution model, just training on the coarser model and then putting it back into the coarse model to see. So basically, the machine learning is finding a mapping between input profiles of temperature and humidity and output tendencies of temperature and humidity. Thanks.
I'm Kerry Emanuel. I'm just going to present a list and let my students fill in the details, but I'm broadly interested in the physics and dynamics of tropical cyclones, which are a wonderful natural laboratory for fluid dynamics and thermodynamics. The intransitivity of tropical climate, are there more than one equilibrium in localized tropical climate for a given forcing? The control of atmospheric water vapor by convection. It's not controlled entirely by large-scale circulation, as some would have you believe. And the dynamics of convection and the role that the sensitivity of tropical cyclones and severe local storms to climate. Thank you.
Hi everyone, my name is Xue Kun. I'm a postdoc working with Romfree, and my research topic is about estimating emissions and using the atmospheric measurement. So we use the measurement data from across the world and use models to relate to the emissions and the concentrations. So we have the measurement data and have the models to estimate the emissions from the surface. So our target is to estimate emissions as accurate and as possible and reduce the uncertainty of the emissions. So finally, we use this top-down estimate to cross-check with the bottom-up reported by each country. So thank you.
I'm Gabriella Farfan. I'm a fourth year in chemical oceanography in the joint program, and I work with Colleen Hansel down at Hui, which is probably why I don't know this interview. But I look at how trace metals that are biolimiting in the ocean are incorporated into tissues and skeletons of corals. And this matters because corals make up the framework of coral reefs. And relatively little is known about how these trace metals are incorporated, and a lot of bulk studies have been done using ICP-MS. But I have this unique access to the Stanford synchrotron radiation light source, and we're able to measure in situ what the concentrations of metals are and where they're distributed among the tissues and the skeletons. So looking here, I have some zinc. This is especially important for carbonic anhydrase and different enzymes, and I can see where it's distributed in the tissues and how it relates to different sulfur ligands, and we can look at the speciation of these things in situ, which is great. Thank you.
Hi, my name is Taofin. I'm in Professor Noel Silling's group. I work on two projects. The first one, we studied climate penalty. We find that the climate penalty is enhanced when we increase the NOx emissions. So the horizontal axis of this figure is NOx emissions. By that, we find that when we decrease NOx emissions, we not only get a lower concentration of ozone, we also get extra benefit from a decrease of the climate penalty, as shown in the middle line of the figure. I'm sorry. The second project I'm working on is to study the hemispheric wind speed decreases phenomenon. I want to look at the role of vegetation, the role of seasonal pattern, and the potential role of urbanization in this regime. Thank you.
Hi, I'm Raf Ferrari, and among the various things that we do in my group, there is one project that is getting us all very excited. It's a schematic I'm drawing here. This is an ocean basin. You see on the left, we know that cooling at very high latitudes tend to form very dense water that sinks all the way to the ocean bottom. The question we want to solve, when you heard Jorn Kallis and Henry Drake talking about various aspects of this problem, is how the waters come back to the surface. And we believe that they come back along very narrow boundary layers, which is something that was not appreciated until recently in the work we've done, and we are trying to tackle the problem with theory, simulations, and now we're also ramping up to collect actually in situ observation to observe the process.
I'm Glenn Swirl, and one of the things I do is not use Microsoft. But I'm interested in geophysical fluid problems in general, jets and vortices in atmospheres and oceans, and working also on the dynamics of mixing to try and understand in detail exact formulations of eddy mixing. But one of the other things we do are visualization intended to present images to the public. This is another form of game. This is an ecological game in which you specify the precipitation, which you saw there, the sunlight, and then you design your organism and you watch it compete with the others to see what kind of trees will be successful.
Morning, my name is Charles Gerler. I'm a second year. I am broadly interested in sort of how Arctic amplification and changes in sea ice cover affect the climate in general, so I'm working on two separate projects right now. The first is with Ron and Erwan Renier, who's a research scientist at the joint program, the other joint program. And for this one, we're essentially comparing members of a large sort of paleoclimate ensemble with the proxy record. There's a really good compilation of proxy data called Pages 2K that we're using, and this is working towards a data assimilation framework for paleoclimate, which is very exciting. I also believe that using estimated paleoclimate states can help us understand the physics of the system. And I'm working on my second project with Paula Gorman, trying to understand the trends in different Lorentz energy cycle variables during the reanalysis period. So that's it. Bye.
Good morning, I'm Daniel Guilford. I'm a fifth year working with Susan Solomon. And we are trying to understand broadly how variability in trace gases, in gases in the lower stratosphere affect the radiation in the tropical tropopause layer, and that in turn can sort of feed back on the climate system and affect the temperatures and affect the other chemistry that's going on in the lower stratosphere. So on the left, I've been looking at the seasonal cycles of ozone and thinking about how the radiative effects sort of propagate down into the troposphere and affect the temperatures there. And on the right, I'm showing a figure that, figure that Carrie made, talking about the intensity of tropical cyclones. And so we think these radiative effects could affect the temperatures right near the top of tropical cyclones, which could alter the intensity of them. So those are the things I'm interested in, and if you're interested in them too, please come talk to me. Thanks.
Hey everyone, I'm Brian Green, a fifth-year grad student in the Marshall Group, and I study rainfall in the tropics, specifically the intertropical convergence zone. Which you can see here in the satellite image as a band of clouds centered right near the equator. And there's a lot of rainfall associated with these clouds. And what we're beginning to appreciate is that by virtue of the surface winds associated with this convergence zone, the ocean circulation that's driven by those winds has an important impact on the energy balance of the ITCZ and its dynamics. So that's what I'm spending my research on. Thanks.
Hi everyone, I'm Mukund Gupta, and I'm a second year student doing two projects, one with John Marshall and one with Susan Solomon. I've often been told that my research looks like abstract art, but I promise there's some science in there too. So the first project with John is looking at the response of the oceans to volcanic eruptions, and we're trying to see whether the deeper ocean has a role in prolonging the response of the cooling we get there. And my second project with Susan looks at the recovery period of ozone, so it's looking at the mirror effect you get between the depletion period and the recovery. So yeah, if you're interested in that, please talk to me. Thanks.
Good morning. My name is Jolene Heiderich, and I'm a second-year student in physical oceanography in the joint program. Currently, my advisor is Fiamma Straneo at WUI, And with her, I'm working on a project called OSNAP, which stands for Overturning in the Subpolar North Atlantic Program. So far, we've been looking at the circulation on the southeast Greenland shelf using hydrographic data and satellite data. And I just came back from a 6-week cruise to the southern tip of Greenland. So those are the pictures that we took there, and we recovered a lot of moorings, so those yellow instruments out there. And we hope with this data we can better understand the dynamics of the shelf breakfront in the region. Thank you.
Hi, I'm Noelle. My name's Noelle, so I chose a Christmas metaphor to describe my work. So I work with Max Saito down at Hui. I'm a third year in the joint program in chemical oceanography, and we're interested in how proteins are regulated in the environment. So much like Christmas trees need decorations to become a functional Christmas tree, proteins need chemical modifications or decorations to make them functional, and so measuring those modifications can tell us something about the activity of those proteins. We're trying to use that activity information to develop biomarkers for key chemical species and transformations of those species in the ocean. So I'll be proposing this thesis tomorrow at 10:30 in the morning. If you're interested, let me know. I'll just see you there.
Hello, I'm Qin Jianjing, a postdoc working with Qian Wang. I'm working on the interaction between Middle East dust aerosol and the India summer rainfall. So dust storm is very active in the Middle East, and their heating effect can modulate the circulation. So the increased circulation can transport more water vapor from Arabia Sea to India, and resulting in more precipitation during India summer rainfall season. Yeah. Thank you.
I'm Brian Kaiser. This is a couple of different projects I'm working on. The one on the top left is a byproduct of my general exam, where I was looking at sea surface temperature variability. And so I went and investigated how well you can approximate that variability with stochastic models. So this is basically showing the black areas are where your time scales are pretty separate enough that a stochastic model works pretty well. The image on the right is a very, very inertial double gyre ocean circulation that's just vorticity. That's kind of a side project I've done just because I like computational fluid dynamics, and I got started on graphs 1201 class. That's kind of an ongoing thing. And then the bottom is a sort of fun but wrong illustration from a paper in the 70s on boundary mixing. I'm interested in the same problems. Raff and Henri and Jörn looking at how internal wave breaking topography and sloping boundary layers are interacting and influence on well.
Hi, I'm Lauren Kipp. I'm a fourth year in the joint program with Physical Oceanographic and Chemical Oceanography. My advisor is Matt Charette down at Hui. And we study radium isotopes, which are added to the ocean at coastlines and sediments, so boundary sources. And then there's 4 radium isotopes that decay with different half-lives, so we can use them to get rates and dates. So for example, we can figure out the age of the water mass or the rates at which trace metals are being applied or entering the ocean. So over the course of my thesis, I've applied these in 2 very different environments. The first is hydrothermal vents, and the second is the Arctic. So last summer, I was on the Geotraces cruise to the Arctic, and I'm working on that data now. Thanks.
Hi, I'm Gekke Murju. I'm the visiting scientist that Sitso mentioned. I'll be working on aerosol cloud interactions in past warm climates. Specifically, I'll be implementing aerosol-dependent cloud microphysics parameterizations and improving parameterizations of ice crystal growth to improve cloud feedbacks in past climates. And I have been, over the past year, I've been dynamically downscaling global model projections on an RSP 8.5 to 3-kilometer horizontal resolution for New England, and I have more than 300 climate variables for New England for the next century and for some historical simulation as well. So if you're interested in looking at this data set, I've been working on changes in extreme events and some impact analysis.
So I'm John, I'm a postdoc working with Mick Follows, and my research is kind of interested in the interaction between ocean circulation, biogeochemistry of the carbon cycle, and how will those affect atmospheric CO2. So whether that's with very long runs of a variety of different models and looking for functional relationships between atmospheric CO2 and things like overturning in the Southern Ocean, or whether we're looking at sort of the steady state and what influences CO2 fluxes, so relating that to heat fluxes and biology and fresh water and stuff like that. And I'm also interested in trace metals.
Hi, my name is Colin McKinley. I'm a professor at the University of East Anglia Tyndall Centre. I'm interested in the global carbon budget, which is the balance between two emission sources, fossil fuel land use change on the one hand, and their partitioning among the atmosphere, land, and ocean. And of these 5 terms, only the atmosphere is well constrained. That's the purple dot to the right. The other terms are estimated from statistics, PCO2, and models. And when you add them up, there's a big gap between the orange and the purple. And I believe we can narrow that gap, particularly with looking at the ocean carbon sink and how we can add constraints of heat flux, oxygen, and carbon together. And I believe there's a lot of expertise here at MIT to do that. But really, the real reason why I'm here for 3 months is because in 1999, I had the opportunity to do a postdoc with John Marshall, which I didn't take to go into an Eastern adventure, and I have been wondering since what I missed out on.
Hi everybody, my name is Willie, and I'm a first-year graduate student majoring in atmospheric science. Sorry about that photo out there. My advisor is Paul Gorman, and previously I studied physics and atmospheric sciences in Peking University, focusing on the banding structure of the joint atmosphere in a quasi-geostrophic model. And right now I'm working on extratropical precipitation extremes, particularly on the vertical structure, and the vertical velocity of those precipitation events. And I'm interested in maybe internal dynamics of extreme precipitation events and climatological impacts, basically why they impact upon the climate. So, thank you.
Hi, my name is Minwei Li. I'm a 4th-year PhD, and I work with Noel Salim, and I study the trans-Pacific transport of air pollutants from Asia to the US, including ozone and aerosols. So in particular, I'm interested in how this process will change in the future, and there are kind of 2 factors that are important. First one is the changes in Asian and subatlantic emissions, and the next one is climate change. And I'm using a modeling approach. I'm using the JUICECOM model, and I also will use the CESM, the Community Earth System model in the future to answer the questions. Thank you.
Well, my name is Eric Lindgren. I'm a 4th-year student. My advisor is Alan Plum, who's not here. But I do stratospheric dynamics, and one of the things that we're working on recently is trying to figure out how to parameterize wave activity to get a realistic northern winter stratosphere in the simplified GCMs. One way to do it is basically just put in a large topography in the troposphere in simple models, but that means that you can't really get a realistic winds in the troposphere. So I'm trying to use heating perturbations around the surface to get the same wave activity. This particular thing didn't work, but some of the math, and it's exciting. So hopefully that can be something that can be used for a lot of different things.
I'm working with, I'm a postdoc since 2 months here, and I'm working with John Marshall and John Michel, learning about the GFD and oceanography. And then working on the Beaufort Gyre up there, but the greenish area. And I'm trying to, we're trying to get with a very simple model of the gyre, which is up on the right. So a mixed layer on the top and a stratified layer at the bottom. The mixed layer is cold, so it's interesting because it's important for the survival of ice at the top and how ice melts coming down. And we have mainly 2 objectives. One is to, on the right, to compare measurements which are in color with the results of the model. So far we can get the upper part, but not the lower part. We're trying to fix that. And the other objective is to find a scaling for the gyre based on the various parameters, the radius, the depth of the layer, and and we are comparing different results from the laboratory experiments up here, so a tank, up to the gyre and the ACC at once down there, and see if we can fit them. I'm running out of time.
Hi, I'm Julia Middleton. I'm a first year in the MIT GUI Joint Program for Oceanography. And so I'm still getting into research, so I decided to talk about kind of where I came from. I went to undergrad at Colby and did a lot of mathematical modeling for virus host ecosystems in the shallow ocean, and then worked in the Caribbean on polycyclic aromatic hydrocarbons, and then worked with the Bigelow Labs doing aerosol data analysis from satellites for the Arctic regions. I kind of did a lot of stuff, and now I'm hoping to work mainly on offshore chemical oceanography and how large amplitude internal waves can bring that into nearshore coral reefs. And ideally, build a model that can couple those effects with the bioresilience of corals throughout a changing climate, because we expect large amplitude waves to be shifting as climate changes.
Thinking we're going to have a break, but I guess we're not. So my name is Paul Gorman. I'm a professor. I study atmospheric dynamics. I'm also interested in precipitation. One thing I'm excited about at the moment is that when it goes to very warm climates, the most unstable mode in the mid-latitude atmosphere changes from a wave with cyclones and anticyclones to this thing, which is called a diabatic Rossby vortex. So the blue and red shading indicates potential vorticity, and then the contours are degeneration by latent heating of potential vorticity, and this thing grows very quickly. Thank you.
So it's 10:20 and we're going to take a break. So please check out, if you haven't done so, at the hotel reception, which is right upstairs. And we'll be reconvening at 10:40, if that's my understanding. And thank you all for presenting. It was great.
Hello. Welcome back. I'm Anne-Willem Onta. I'm a research scientist in the McFollows group. And lately I've been working on this project, understanding the biological carbon pump through plankton physiological modeling. Now first, what is the biological carbon pump? Well, maybe first, what is it not? So the biological carbon pump is not the rate at which anthropogenic carbon gets transported into the deep ocean. Let's clear that up first. So what is it? Essentially, this is an old picture that I made long time ago. So phytoplankton grows at the ocean surface, takes up nutrients, and carbon sinks into the deep ocean is they're remineralized into inorganic nutrients in carbon, and then that carbon is transported back up by physical processes. Now, what is very important in the process is the chemical composition of the phytoplankton, how much carbon is being bound per amount of nutrients, and that is why we do the physiological modeling, figuring out the chemical composition of phytoplankton. Thank you.
Hi, my name is Astrid Puccini. I'm a first year in the joint program in physical oceanography, and I'm working with Bob Pickard down at Hui. So in the past, we've worked on Chukchi Sea and overturning and circulation off of the shelf into the Arctic Ocean. And now I'm switching regions and looking at, like Jolene, the overturning of the Subpolar North Atlantic program, or OSNAP. And in particular, I'm focusing on the East Greenland coastal current, which you can see here denoted by the red velocity vectors. Those are integrated over the entire water column. And we're particularly interested, you can see in the vertical sections on the bottom right panel figure that it's associated with a large freshwater plume coming off of the Greenland glaciers. So we're interested in the dynamics of this flow around Greenland, and particularly what happens off of the coast of Cape Farewell, so the very southernmost tip of Greenland. Thank you.
Ron couldn't be here and asked me to fill in. Unfortunately, I haven't seen the slide before, so you can tell from the two roulette wheels that Ron spends much of his professional time gambling. And you can see from the bottom chart that the gambling proceeds are used to maintain an elaborate network of trace gas treatment stations located strategically in all the best vacation spots. If you really want to know what Ron does, do talk to his students and postdocs, many of whom are here today.
Great. Hi everyone, I'm Deepa Rao. I'm a third year in the MIT Hui Joint Program working with the Follows group. What I'm interested in is the role that mutualistic interactions play in phytoplankton distribution and community structure. For the past several decades, oceanographers have been focusing on how inorganic nutrients like nitrogen, phosphorus, and iron shape phytoplankton distributions, but we know that organic resources are also important to the community structure and function. The case that I'm focusing on is B12, because most eukaryotic phytoplankton require B12, but none of them can produce it. It's only made by bacteria and archaea. So there's this inherent dependency in the microbial community on this vitamin exchange. So to approach this, I'm developing a series of models starting with cobalt cycling, because that's the central metal cofactor of B12, building up to the exchange of carbon and B12 between prokaryotes and eukaryotes, and then ultimately understanding how these interactions shape the community structure. And if you're interested in any of this, please come talk to me.
Hi everyone, I'm Mallory. I'm a first year at Chemical Oceanography. I'll be working with Alec Wang on marine carbon cycling and autonomous DIC pH high resolution sensors. I'm also trying to finish up some secondary projects from my master's at Syracuse University. I worked on carbonate chemistry, clumped isotope geothermometry, and desert soils. In particular, we worked in the southern central Andes of Argentina and Chile, where we were trying to figure out seasonality of carbonate formation in these regions so that we can better relate surface temperatures to the clumped isotope records that we're actually getting. We're also trying to figure out some site-to-site variability, which is a little bit inconvenient because we're looking at sites that have basically all the same soil and vegetation and elevation characteristics, but can still show a 10-degree or more difference in clumped isotope records, which is a huge problem if you're a paleothermometry anything. So, thank you.
Hi, I'm Michael Rush, postdoc in Dan Zitzer's group, second year. I'm working on the separation of ice crystals and cloud droplets in the real environment. And that's why we're building up right now these phase separation inlet system, which would be unique in the US continent. There are some in Europe and other parts of the world, but not in the US. And the important thing is that the instrument called LDCVI, a pumped countable virtual impactor on the right, you can see how it works, will be 3D printed with our 3D printer and all that. And down there, this is a 3D printed particle generator, because we have to also generate particles in our lab to study them. So this is fully 3D printed and shown this here, like the fluid aspect, how it's bubbling and can generate particles. So if you're interested in that, come down to the 13th floor and see the 3D printer in action. Thanks.
Hello, my name is Karen Rush, and I am also a postdoc in the CISOS group, and I'm working in a joint program with Saudi Arabia, and we're interested how solar cells are affected by dust particles. And the most important thing is that the dust can vary from location to location, mainly for seeing how solar cells work and how they are affected by dust. Arizona Testis was used, but we are especially interested in natural dust, which we collected in Saudi Arabia, and this dust is then deposited on solar cells, and we are interested in how the efficiency of the solar cells is decreased, for example, by the size of the particles, by the shape of the particles, which we are seeing in images from electron-scope microscopy, or which we can actually put into our palms instrument, which maybe will Maria later on demonstrate, and see how the chemical composition of the particles differs and how they are affect the solar cell efficiency. Thank you very much.
Hi. So I'm a first year PhD student with the group of Curie Manual. So I haven't really started research yet. In my master's project, I was working on mesoscale mid-latitude meteorology. So more specifically, deep convection initiation. These were modeling-oriented projects and basically used method of Lagrangian analysis of model outputs, tracking the clouds. Now I'll be working on tropical meteorology, still modeling-oriented, and it will be treating, at least initially, of the superintensity in simulated tropical cyclones. The first goal will be determining the role of the numerical schemes in the superintensity. Thank you.
Hi, I'm Jeff Scott. I'm a research scientist in PAOC and the Center for Global Change Science. We're interested, this is work with John Marshall and some of the people in his group. We're interested in understanding what's going on in the Arctic with which seems to be undergoing rapid climate change from the ocean perspective. And we are coordinating an intermodal intercomparison program where we're looking at very simple, idealized forcing anomalies to sea level pressure, wind in the Beaufort Gyre and the Greenland Sea, looking at the river runoff into the Arctic and properties of the inflow into the Arctic. And what we're really trying to do is not only understand the basic mechanisms in science, but also look at some of these structural uncertainties of these models and really understand what's controlling the time scale for the response and the magnitude of response. So, thank you.
Student at Curie Manual, and I study environmental conditions in which secondary eye walls sometimes form in hurricanes. So there's an image taken from a microwave satellite. You can see that there's a concentric ring of enhanced convection and radiation from the primary eye wall. And we care about these because in the last 30 years, people have gotten much better at forecasting where hurricanes are going to go, but it's still very hard to forecast their intensity. And the formation of these secondary eye walls and the way they replace primary eye walls are associated with fluctuations in intensity. So I'm looking at model data and experimental data to identify environmental conditions in which they form, and also how those conditions are different from what hurricanes just tend to influence.
Hi, I'm Susan Solomon. I'm a professor in atmospheric chemistry and climate science. We're interested in lots of things in the group. You've heard from some of my colleagues. Jim and Amy talked about the work on agriculture and water. We're also doing some interesting work on public opinion. We collaborate widely within and outside of MIT. A lot of our work is still on chemistry in the stratosphere and troposphere. We're having a lot of fun with Antarctic ozone and its recovery, as well as volcanoes. One of the cool new results that we have is illustrated on the bottom there, which is I've always been interested in timescales of climate processes that really fascinate me. And so what we're looking at there is what happens if you increase methane and then abruptly stop it. You can see what happens to the radiative forcing on that side. And the title of the paper is Centuries of Sea Level Rise from Short-Lived Greenhouse Gases. And as you can see, that's what you get with the thermal expansion effect. And really proud of Daniel Guilford because he came up with some very clever aspects of interpretation of this in terms of ocean heat uptake and climate feedback.
Hi, my name is Will Piero. I work with Amala Mahadivan, a scientist at WUI. My project focuses on the air-sea interactions in the Indian Ocean with motivation to better understand the intraseasonal oscillations in rainfall and monsoon convection. So we switched from very sunny periods to very active periods with strong winds and lots of rainfall. The seasonal rainfall pattern is determined by these intraseasonal oscillations. And so our project has done a lot of observations with in situ hydrographic data of the Bay of Bengal, and we're now trying to both analyze that data and use some modeling to understand what is the ocean stratification role in setting SST and how the system is coupled with the atmosphere.
Hi, I'm Eric Stansfer. I'm a fourth-year graduate student with Dan Rothman, who is not here, which is too bad because these results are brand new. This is a numerical simulation of 5 rivers growing under influence of water coming from the top flow into the Nirvana. You can see they're basically trying to spread out, which makes sense. Last year, I'm sure you all remember my research roundup slide where I presented a theory involving these, and I'm hoping that numerical simulation agrees. We'll find out soon. All right.
Hi, my name is Kane Stone. I'm a relatively new postdoc here working with Susan Solomon. So last year there were 2 kind of significant events in the Southern Hemisphere. There was a large volcanic eruption in Chile and also a record low ozone hole. So I'm looking at the extent of the influence of this volcanic eruption on ozone depletion in the stratosphere in the Southern Hemisphere. And I'm doing this using both observations, ground-based, satellite and balloon-borne, and also with the specified dynamics version of WACCM. And you can see this sort of qualitatively in the plot on the left. So this is South Pole, which apparently I think is in the Northern Hemisphere with that double negative. October ozone suns in a pressure region that is influenced heavily by volcanic aerosols. And you can see 2015 was the lowest year since Pinatubo, which is the other red dots around 92, 93. And the plot on the right shows deviation from the 2004-2014 mean for both satellite observations and the model. Thank you.
Hi everyone, I'm David Talmy. I'm a research scientist working with Nick Follows and others. I'm interested in microbes generally and how to understand interactions between different microbes and how they scale up to large-scale processes. So here are some pictures of these guys. The guys on the left are autotrophs, they're photosynthetic. The guys on the right are heterotrophic, so they have to get organic forms of carbon and other nutrients. And then this is a model based on interactions between those two, surface ocean annual averaged particulate organics carbon to nitrogen ratio. And more recently I've been thinking about viruses and how they may also play a role in these kind of large scale plans. Thank you.
Hi everyone, my name is Catherine and I'm a second year PhD student. And I'm mainly interested in several anthropogenic impacts on atmosphere and climate, mainly from a modeling perspective. My advisor is Susan Solomon, and my primary project right now is on the rates of heterogeneous chemistry in the monsoon region. And I'm also doing my secondary project with Tim Cronin, and if anyone is interested in talking about any of that stuff, or just talking in general, come up to the 17th floor. I know it's high up there, but I promise, yeah, we're not too scary there.
Good morning. I'm
I'm Martin Wolf. I'm a grad student in Dan Sitsos lab. The atmosphere is full of so many wondrous types of clouds, which are made up of water droplets and ice crystals. And the ice crystals in turn form in the atmosphere by and large when water vapor freezes or condenses around certain types of aerosol particles, which are called ice nucleating particles. So mineral dust is one really commonly studied type of ice nucleating particle, and our lab does a lot of studies on that. Recently, I've been getting into a research project where we study how the inorganic and organic components of seawater, so the organic components produced by phytoplankton, can also aid, or I guess they can also act as good ice nucleating particles in the atmosphere. We're trying to quantify that. So stop on by the 13th floor and I'll show you my cloud chambers.
All right, we have 3 Z's this year, so we're almost done. So I'm a 6th year. I work with Nick Follows, and I'm working on how, so we know that microbial metabolisms control large distributions of oxygen, nitrogen, carbon to a large degree, and so are related to the climate system. But those processes are represented very simplistically in climate models. So what can we do about that? So I'm using the underlying chemistry of these microbial metabolisms as a systematic framework to do that. So this is an example of this in action. At the bottom is a minimalistic oxygen minimum zone. We have 2 microbial metabolisms, aerobic and denitrifying microbes, interacting to deplete oxygen and dynamically denitrify nitrogen from the ocean.
I'm Maria Zawadovich. I work with Dan Sitso, and I work on mass spectrometry, in situ mass spectrometry of single aerosol particles. All aspects of it, from instrument development to field deployments to detailed analysis of the output. This is our single particle mass spectrometer. It's called particle analysis by laser mass spectrometry. Here is its photo in the lab. Here is its schematic. Recently, I've been working on trying to see whether or not this data will help me to determine if there's biological material in the atmosphere. I will, thanks to everyone who came to hear me speak about it the other week, and I'll be hopefully talking about this more. And here, in the near future, I'm hoping to be able to miniaturize this instrument so that it can fly on a small aircraft or UAV.
Hi everyone, I'm Cheryl Zerbrick. I'm a postdoc in Ed Boyle's lab, rounding out my 2nd year at MIT. I've studied lead and lead isotopes, stable lead isotopes, in the ocean, in the Arctic, Southern Ocean, Atlantic, and South Pacific. And here are results from the South Pacific. They were the hardest ones to get, so that's why I'm showing them. The rainbow colors here show a transect mirrored up above on the map from the coast of Peru out towards Tahiti, with the rainbow colors, reds being higher concentrations and the purple being almost no lead in the ocean. And the East Pacific Rise, there is a hydrothermal vent site, and so as the water flows past it, it seems that most of the lead is scavenged out of the water column, making it exceedingly difficult to measure lead isotopes on no lead. But I've done it, and so in the plot here, depth on the y-axis, we see a definite change in lead 206, 207. It's kind of like a fingerprint analogy. And so we see it change after it goes past the hydrothermal vent. And so we're just generated this result about 2 weeks ago, and now we're trying to decide what all it means. And now onto business. Before we move on to State of PAC, we have huge thank yous to those who helped organize the retreat this weekend. So as I call your name, please stand up. Martin Wolf. There he is, our Wonderful. We hope